Okay, welcome back. In this section, we're going to look at the relationship between a quadratic equation, like we've been working with for the last few units, ax squared plus bx plus c, and what its graph looks like. So by the end of this unit, you're going to be able to take a quadratic equation, know what its graph will look like kind of in your head, and then also how that graph ties to the solutions that we found and the discriminants. So this section is going to tie together several of the ideas from our last two topics. So the first thing to recognize is that anytime you have a quadratic function, and by the way, we're replacing 0 with f of x now. We're going to treat this quadratic not as an equation so much as we are a function where we can plug in values for x and then get some output value. So if we graph these functions that are quadratic, we will always, every single time, get a parabola. And that should be no surprise because they are based on one of our base function was f of x equals x squared. And of course, that's the simplest parabola at all. That's one of your many base functions that you already know. So that means every parabola that we have is going to look like one of these two at the bottom of your screen. A little bit of terminology. First of all, the vertex. The vertex is the name for the tip of the parabola. It's the lowest point if it opens up, or it's the highest point if it opens down. The axis of symmetry is that line that goes right down the middle. These are all important aspects of our graphing, which we're going to do in a minute, but the axis of symmetry is just a line down the middle of the parabola. And then the last thing to note is that every parabola that we work with will either open up or down. This allows it to pass the vertical line test so that we are in fact dealing with functions. If we had a parabola that was lying on its side, which you can have, but we're not going to work with those in this class because those fail the vertical line test. A vertical line would hit in two places, and that's not a function at all, so that becomes a bit more complicated. But the thing that I want you to note here is that whether or not the parabola opens up or down depends completely on our coefficient a. If a is bigger than 0, that is to say positive, that parabola will open up. And if a is less than 0, that is to say, if it's negative, then it's going to open down. So we can just look at a quadratic and know which direction it's going to open. But there's more to graphing a parabola than that. Okay, so in general, there's a 6-step process that we go through when we go to graph a parabola. And I'm going to do an example and walk through these 6 steps. So I'm going to bounce back and forth. Since we have limited space here, I'm going to bounce back and forth between our graphing screen and these 6 steps. A little bit of one other thing that we need to note here is that universally, going back to when we worked with transformations as well, we saw this, but we will call the vertex of the parabola, we will call those values h and k, and those are the x and y coordinates of the vertex. So let's go ahead and look at an example and explore these 6 steps. Let's consider this function. F of x is equal to x squared plus 3x minus 10. Note here that based on the coefficients, we have a coefficient of 1 in front of that x squared, so we would say that a is 1, the b value here is 3, and the c value here is negative 10. So let's graph this by determining its orientation, its vertex, its axis of symmetry, and all of the intercepts. So step 1. We want to determine whether this parabola opens up or whether it opens down. And we're going to pay attention to our a value. Since our a value is equal to 1, and that is obviously a positive number, we know that this parabola will open up. Now we'll figure out where this parabola is located. Step 2, we want to find the x-coordinate of the vertex. Here again, the x-coordinate is called h. This is a place where we're going to use what's called the vertex formula. The vertex formula says that h, that x-coordinate, is found by taking negative b and dividing it by 2 times our a value. So let's do that. H is equal to negative b over 2 times our a value. Based on our coefficients, that means we're going to have negative 3 divided by 2 times our a value of 1. Or in other words, negative 3 halves. So that means that our x-coordinate is going to be 1.5 units to the left of the origin. We have to figure out how high or low that is by finding our k value. To find the y-coordinate of the vertex, we take that value that we just got, negative b over 2a, and we plug it into the function. So we're using our function notation here. That gives us the k value, which is, of course, the y-coordinate of the vertex. Let's do that. So the other part to finding our vertex here is to find our k value. And so to find our k value, we're going to plug our h value, negative 3 halves, that's an x value, and that'll allow us to find the corresponding y value. So that means our k value is going to be equal to negative 3 halves plugged into the f function, and so based on our function up here, that's going to be negative 3 halves squared plus 3 times negative 3 halves minus 10. This is a good time to use the fraction button on your calculator, and if you compute that value, what you'll find is that k is equal to negative 3 halves squared, that's going to be 9/4, plus 3 times negative 3 halves, that's minus 9 halves, minus 10. And if you do that, you get negative 49 over 4, or in other words, negative 12 1/4. So what we've found is that our vertex must be located at negative 3 halves, negative 49/4. Or if we want to put those into mixed numbers to make them a little bit easier to think about, that's negative 1 1/2 and negative 12 1/4. Okay, so that means our vertex is 1.5 units to the left and down 12 1/4. That barely fits on our screen. That's going to be right about there. And we know that this parabola is going to open up from there. The fourth thing we can note is that our axis of symmetry, the line of symmetry, has to go right through the vertex. It's going to be a vertical line through negative b over 2a. And so that means that our axis of symmetry is going to be 1.5 units to the left of the origin. It's going to be right there. That's going to be right down the middle of our vertex, and I'm going to call that AOS for axis of symmetry. That was our fourth step, and that leaves us with 2 more important pieces of information we can find about this parabola. The fifth thing we can find is our y-intercept. The y-intercept is the value of the function when we let x equal to 0. As always, with lines, when we find the y-intercept, we let x be 0. If we let x be 0, then what we're doing is we're calculating f of 0, which will be 0 squared plus 3 times 0 minus 10. And that, of course, is negative 10. So that tells us that our parabola has to pass through the point 0, negative 10. Because an input of 0 yields an output of negative 10. That's a point on our parabola. So we can plot that right here at 0, negative 10. That is our y-intercept, and we know the parabola has to pass through that. Now, note here that we have another point for free. That point is 1.5 units to the right of the axis of symmetry, so we must have a matching point 1.5 units to the left. And so we'll have another matching point right there, and the parabola has to pass through that point. Now we're starting to get an idea of what our parabola looks like here, but there's one more important piece of information that we need. And that is, we need the x-intercepts. And when we go to find the x-intercepts, of course, we're going to let y be equal to 0. And that's if there are any. Not every parabola has x-intercepts. So what we're going to look for are the values of x that make f of x equal to 0. That is to say, we're going to set our quadratic equal to 0 and solve it like we have in the last two topics. Let's do that. So to find our x-intercepts, we're going to let f of x, or in other words y, be equal to 0. So then this means we need to solve 0 equals x squared plus 3x minus 10. And of course we can solve that using the quadratic formula, by factoring, by completing the square. This one factors pretty nicely, so let's just do that. We get 0 equals x plus 5 times x minus 2. And so we have two solutions here. X plus 5 equals 0 means x equals negative 5. And if x minus 2 equals 0, then we can conclude that x equals 2. Now in both of these cases, y is equal to 0, so we have two x-intercepts. They are negative 5, 0, and 2, 0. And we can plot those. The first one, negative 5, 0, is going to be right there. And our other one, 2, 0, is going to be right there. Now take a look at that, and what you should notice is that they should be the same distance from the axis of symmetry. This one on the left is 1, 2, 3.5 units from the axis of symmetry. And the other one is also 3.5 units from the axis of symmetry. That's good. They should be symmetric around the axis of symmetry. And what that also means is that we now know pretty much what this parabola looks like. It's going to pass up through the point 2, 0, and it's going to pass up through the point 5, 0. And there's our parabola. The thing I want you to notice here is that the solutions, which is what we've been working in the last few lessons, the solutions to that quadratic are the x-intercepts on the graph. And so sometimes there are no real solutions, and that means the parabola might not have x-intercepts. We'll see that in another example in just a minute. Okay, I've got this problem labeled as a practice problem. If you want to pause the video and go ahead and try this one, you can sketch yourself a piece of graph paper and see if you can find those 6 aspects of what this parabola is going to look like. Let's go ahead and take a look here. So we're going to go through the same 6 steps, which means I'm going to jump around just a little bit. Okay, first of all, let's determine whether or not this parabola opens up or down. If we take a look at the function we're given here, you can see that our a value is negative 3, our b value is 6, and our c value is negative 5. Because our a value is negative 3, that's a negative number, this parabola will open down. Next, let's find the x-coordinate of the vertex using the vertex formula, h equals negative b over 2a. In this case, we have negative b, which is negative 6, over 2 times our a value, which is negative 3. And so we get negative 6 over negative 6, that is 1. Now let's use that value of 1 to go ahead and find the y-coordinate by plugging that number into our function. I just noticed a little error here. I accidentally said x equals negative b over 2a. It is the x-coordinate, but we typically call that value h. Now we're going to find k, which is f of that value. In this case, that is f of 1, which is going to be negative 3 times 1 squared plus 6 times 1 minus 5. And if we compute that, we get negative 2. And so we can conclude that our vertex is located at 1, negative 2. 1 to the right and 2 units down. There's our vertex. Now we know that this parabola is opening downward, and so we know that it must be curving downward through the vertex. Step 4 is to now mark the axis of symmetry, which travels right through the x-coordinate of the vertex. And so our axis of symmetry must be right along the line x equals 1. There's step 4. For our fifth step, we're going to find the y-intercept. Now notice that when we plug 0 into a function, everything will cancel except our c value. Let's take a look at that. In our previous example, when we plugged 0 into this function, we got 0 plus 0 minus 10. Turned out to be our c value. That's always going to be the case. Just like in a straight line where we know y equals mx plus b, and b is our y-intercept, the constant at the end is always the y-intercept. So we know that our y-intercept is going to be located at 0, comma, -5. And that means we can plot that point. 0, -5 is right there. That's a unit to the left of our axis of symmetry. There must be another point, a unit to the right. And we know that our parabola has to pass through those 2 points. And our last step is to find the x-intercepts, if there are any. So to find the x-intercepts, we're going to let f of x equals 0. That is to say, we need to solve 0 equals -3x squared plus 6x minus 5. Now, take a minute and look at your parabola. Look at where it lies. Is this thing going to have any x-intercepts? Is that ever going to cross the x-axis? No, it's not. But let's go ahead and try solving this. Let's use the quadratic formula this time. The quadratic formula says x equals -b plus or minus the square root of b squared minus 4ac all over 2a. And so in our case, x is equal to -b, which is -6, plus or minus the square root of 6 squared minus 4 times -3 times -5, all over 2 times our a value, which is -3. If we clean that up, we get x equals -6 plus or minus the square root of -24 over -6. Now, 2 things I want you to notice here. First of all, those are going to give us imaginary solutions. If we take this a little bit further, we have -6 over -6 for our real part. That is 1. But of course it is. Look at this. -b over 2a, that is our vertex formula. That's how we got our axis of symmetry and the x-coordinate of our vertex. Now the square root of -24, we can factor a 4 out of there, and that is 2 square root of 6 over -6i. But the negative rolls in with this plus or minus, and the 2 over 6 cancels, and we get 1 plus or minus the square root of 6 over 3i. There's our solutions, but those are imaginary, which tells us it never does cross the x-axis. We can't plot that. And so we can conclude here that there are no x-intercepts. Both because we got imaginary intercepts for our solution, and because the graph clearly shows that the parabola never hits the x-axis. Okay, there's one more example that I'd like to work through with you before I turn you loose. Let's graph this function, -x minus 3 squared plus 4, by doing the same 6 steps. Well, this one we have a little bit of work to do. So let's start with our function f of x and rewrite this. We have to FOIL out that x minus 3 squared plus 4. We have to do that, of course, because we need our function to be in the form ax squared plus bx plus c in order to use our vertex formula and find the y-axis. So let's do this. This turns out to be negative x minus 3 times x minus 3 plus 4, or in other words, negative x squared minus 6x plus 9 plus 4. Negative sign gets distributed in. We have negative x squared plus 6x minus 9 plus 4. And that means our function, when it's in the form we want it to be, is equal to negative x squared plus 6x minus 5. So I'm going to rewrite that function up here so that we have reference to it. F of x is equal to negative x squared plus 6x minus 5. You'll have some work in WebAssign where you'll need to do that rearranging to get it in standard form before you begin, so watch out for that. Now let's go through our 6 steps. I won't flash back this time. They're the same 6 steps we've had before. Notice here that our a value is equal to negative 1. And so we can conclude that this parabola opens down. Our next step is to find the vertex. So the h value of our vertex is the first part of the quadratic formula, negative b over 2a. We just don't have the plus or minus square root done there. And in this case, that is negative 6 over 2 times negative 1, since our b value is 6. And that works out to be 3. The other part of our vertex, the k value, is found by plugging that into our function. So we want to find f of 3. Negative 9 plus 18 minus 5 turns out to be 4, and therefore we can conclude that our vertex is at 3, 4. So we can plot that, 3 right, 4 up. There's our vertex. We already established that this thing is going to open down. Tell me right off the bat, are we going to have x-intercepts this time? Yeah, we are. This parabola is going to open down and cross it into our x-axis in a couple of spots. All right, step 4 is to identify the axis of symmetry. It's got to go right through the vertex. So there's our axis of symmetry. I'm slightly off the line there, but we're pretty close. And step 5 is to find the y-intercept. And we know that we can let x be 0, but it's predictable what we're going to get. Our y-intercept, when we let x be 0, is going to turn out to be just the constant at the end. And so 0, negative 5 is our y-intercept, and we can plot that. Now notice that that is 3 units to the left of our axis of symmetry, and so we must have another point 3 units to the right of that. Now that leaves us with finding our 2 x-intercepts. We can see that this parabola is going to have to cross 2 times. Let's figure out where that happens at. Okay, to find our x-intercepts, we're going to let f of x be 0, or in other words, we need to solve 0 equals negative x squared plus 6x minus 5. Okay, let's do that. Let's use the quadratic formula here. X equals, I won't write out the quadratic formula, we've used that a bit. X equals negative b, which is 6, plus or minus the square root of b, which is 6 squared, minus 4 times a, which is negative 1, times c, which is negative 5. All over 2 times an a value of negative 1. So that turns out to be negative 6 plus or minus the square root of 36 minus 20 turns out to be 16. There's a case where our discriminant turns out to be a perfect square. And so we are going to get rational results when we simplify this. That goes back to our last topic. Okay, and that's all divided by negative 2. So a bit further with that, negative 6 plus or minus 4 over negative 2, which becomes negative 10 over negative 2, or negative 2 over negative 2. Simplify each of those, and we get x-intercepts of 5 when y is 0, and the other one is 1 when y is 0. And we can plot those. Those are right about where we'd expect them to be. We can kind of see where this parabola is going to have to crash through our x-axis. And it's right about where we would have expected. And so we found all the intercepts. We are done with this example as well. Now I want to look at that example one more time, but take a different perspective on it. You know that the base function, as we kind of started the topic out, the base function for x squared is a basic parabola through the point 0, 0, and 1, 1. Hopefully you haven't forgotten that. And so that parabola looks generally like that. Now, take a look at the function we were given. Before we went and FOILed out that exponent, we've done this problem before, but we treated it as a transformation. So let's do that here. Let's take our function and apply the necessary transformations. The first transformation we would apply to this would be to, by the order of operations, apply the parentheses and make that x minus 3 squared. Now, what would that do to our base function? Well, that negative 3 on the inside does what? Move it left, right, up, or down? Well, that moves it to the right 3 units. And so that would take our base parabola and move it 3 units to the right, so that our parabola would now be right about there. The next thing we would do is flip that thing over, and our function would become negative x minus 3 squared. That means we're going to take that parabola and flip it upside down, which is going to put it right about there. And our last transformation would be to take that base function, f of x equals negative x minus 3 squared, and we would add that 4 to the end. And of course, hopefully you remember that that moves us up 4 units. So if we take this parabola and move it up 4 units, it takes our parabola and moves it to right about there. And so that black parabola, that is our last one, that is the very same one we graphed just a minute ago. There it is. It was in red in this example. It's the exact same parabola, but we got to it in a slightly different reasoning here. We treated it as a transformation instead of using the vertex formula as we did here. So we could handle that both ways. So this is actually the last topic in this unit. The things that you need to make sure that you can do are know that you can graph a quadratic, that h and k are the location of the vertex. We can use the a value to determine the orientation of the parabola, that we can use the vertex formula to find the h value and then plug that into our function to find the y value. We know that the axis of symmetry has to run right through that x value, that the c value on our quadratic, that's the value that tells us our y-intercept. And if there are any x-intercepts, they are found by setting the function equal to 0, and then we solve the resulting quadratic. Your assignment should be available to you now. Go ahead and go after that, and make sure to reach out if you need help.